Hello, everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm your host for today's session. And just as a heads up, this is not a beginning class on harmonics. And with that said, it's a very enjoyable presentation. Before I introduce our speaker for today, we'd like to run a couple poll questions just to get some feedback from the audience. And as always, there's no obligation or liability. First question is, an IBR is an inverter-based resource. And the question is, how often do you need to evaluate an IBR-based power plant for harmonic performance? Okay, looks like we're at our quorum point. Here's how folks would weigh in on this question. All right, thank you. And then the second question is, which compliance standard is required by the utility companies you work with? And this is multiple choice. As I indicated, this is not even a PowerPoint presentation. It's an actual discussion using the tools to deal with the topic at hand. And we are recording the session because you may want to review it at some point in time as you're trying to recreate the material presented. So bear in mind, we will have a Q&A session afterwards. All right. Again, thank you for joining us today. Here's how folks have weighed in on this. And so our guest speaker today is Dr. Tao Yang, who's principal engineer here at EasyPower. And give me just a second and I'll hand over the baton. Dr. Yang, you have the floor.
Yeah, share my screen here. Can you hear me okay now?
Yes.
And see my screen?
Yeah.
Okay, wonderful. Thanks again, Jim. And good morning, good afternoon. This is Tao Yang from EasyPower. I'm the principal engineer here, working on the power system application development. And sometimes I also get the engineering support questions or engineering support projects from our premium clients or premium licensed customers, and also our other customers who would like our engineering help. So we got quite a few harmonic study projects from the industry. So I think it might be good to bring the contents of what we have learned or what the typical process we use to evaluate the harmonic injection or harmonic performance analysis in the renewable power plant. So I think mass majority of EasyPower customers focus on the harmonics issue in the industrial plant level. And as we all know, that renewable generation, especially the IBR-based generation of power plant at the utility scale, is getting more and more penetration level, I would say, all over the North America, all over the United States. So there are more and more I would say projects coming on focusing on the IBR-based harmonic performance. And this is just one simple example to show that what the typical process of building the model in EasyPower and evaluate harmonic performance. And eventually we want to talk about what kind of the mitigation plans typically we used to mitigate violations, standard violations, if there is any. And as we all know that, maybe not all of us, but at least some of us may know that IEEE 519 has just released 2020 back in August. So starting from that time, there will be a decision tree, which we'll talk about later in the IEEE 519. So IEEE 519 will no longer be the only standard applicable to the industry, especially for renewable power plants. Some people still use the IEEE 519. Again, that's why we have this poll question, that what kind of standards do you still use? Or does your utility, local utility you connect to, still use over here? Either the IEEE 519. If you are using IEEE 519, then definitely you want to comply with the latest IEEE 519 projects going forward, right? But I also understand there are some existing projects still use the old 519 as the agreement the project established, which is okay. So more often, we will say more and more IEEE 2800 has been used as a harmonic standard as well for the IBR-based power plant. And IEEE 519 2022 also mentioned that the applicability of the 519 1547, which is a DER standards, and also the 2800. So we will talk about first of all, how to model the projects, the IBR-based power plants in EasyPower, and which includes power flow model, which includes short circuit model, and also the harmonic model in EasyPower. Keep in mind that IEEE 519 is still sensitive to the system strength, which is system short circuit ratio, measured at the point of common coupling, right? And starting from the IEEE 2800 and the 1547, short circuit ratio, which is a system strength, is no longer in the standard or in the criteria picture. So that's a big change to the applicability of the 519 and the 2800 and 1547. We may be able to talk about that at the very end, but that's just some preface we want to place at the beginning when we talk about the standard, because at the end of the day, what we're doing is to make sure that our inverter-based resource plant harmonics performance is within the criteria that you as a utility company has established and agreed on, right? So which standard to use, or even have your local standard. I saw from the poll that there are some cases that are using some standard established between you and the utility separately, which is okay. Again, those standards are just IEEE standard. There is no police after that. So it's more about what standard you would like to adopt and use here. So that's a preface we want to discuss at the beginning. And now let's get into the power plant design. So the one I showed at the first in front of you is the typical renewable generation, IBR-based renewable generation power plant. It's a very popular solar plus energy storage combined. People call them as hybrid power plant, right? So you have 6, 6, 6, and 5, which means that you have 23 PV panel and a PV inverter to produce the PV portion. On the other hand side, you have 1, 2, 3, 4, 5, 6, 5, 5, 5, which means that you have 21 battery energy storage inverters. So it's a hybrid power plant consists of both the PV portion and the BESS portion. And definitely, they use different inverters, even though the manufacturer is SMA, right? SMA is one of the, I would say, most popular inverter manufacturers in the United States, together with Sungrow and from other manufacturers as well. So we use the SMA as an example. So what we first need to collect the data from either utility or the facility design is the one-line diagram, right? That will describe how it is, the project is connected to the utility, how the project is constructed. You have the main power transformer. In NERC's world, it's called as a substation transformer, right? In many utility, people call them as main power transformer. And then you have your collector system, collector cable equivalent. I think we discussed the collector cable impedance equivalent in some webinars we have had like 2 or 3 years ago. If you have interest, please feel free to browse back to say how to equivalize the collector system equivalent. But here, since we are doing this harmonics but in detail, so we have to model every collector cable explicitly instead of having an equivalent system to represent, right? And at the very end of this collector cable system, you have the pad mount transformer. Some people call them as GSU. So again, different people have different preference of the terminology, which connects the inverter usually at 0.69 kV or 0.6 kV up to 34.5 kV. So that's your step-up transformer or pad mount transformer to collect your inverter together to the 34.5 kV. So all those things should be explicitly modeled in EasyPower to evaluate the power plant harmonic performance, right? So this is the one line we need to consider and collect first. Now, the second question or second data we need to collect is the power flow data. Again, harmonics is another set of power flow, right? So it's based on power flow. So you're gonna have to collect the main transformer, such as your base rating, which is your MV base, right? And the corresponding impedance, XR ratio for you to construct your power plant. it's not 100% necessary that you collect the high to tertiary or low to tertiary impedance, because we can always use a two-winding transformer to represent the main transformer, right, for the harmonic and the power flow study. Do you have a capacitor bank? We'll talk about how the capacitor bank would actually harm the harmonic performance, because in many cases, people would like to use the capacitor bank as a static reactive compensation equipment to meet the FERC order 826 requirement, which is a 0.95 power factor measured at the high side of substation transformer, right? But it's not always a good idea. I mean, I actually personally, I don't like the idea at all of using capacitor bank at a 34.5 kV to compensate for the reactive power losses in the station, because that will create a resonance, right? You have a charging, you have a capacitance between your phase to ground. And by natural, together with your series impedance, such as a collector cable, transformer, etc., that's an LC network. So it's very easy to introduce, I would say, resonance points in your network. And at some cases that you may have high order harmonic, or not even high order, maybe 8th order or 9th order, or maybe 11th order harmonic current injection, the current torsional harmonic current torsional distortion into the system, so which is going to be a violation as well, right? So we don't have a capacitor here, which is good. Solar inverter, we use the SMA SC4000. Solar inverter step-up transformer, which is a GSU, right? And also the battery energy storage inverter, we use a SMA SCS3950. And that's pretty much it. And also the energy storage inverter step-up transformer. That's pretty much it, all the information you need to model the power flow model of your network. Now, other than that, you also need harmonic spectrum from the manufacturer, right? This is obviously the most cumbersome work that we have to do, is to ask the right people to the right information. For SMA, it's easy because we know that SMA provides a very, obviously, robust data support of what we need. In fact, for the inverters, they all provide very detailed harmonic spectra for the inverter that they manufacture. So this is what we typically would need to request from our, I would say, manufacturers about what's your harmonic injection spectra, right? You can see that it looks like very exactly the same as what EasyPower would take as an input. What is your harmonic order? The second, 4, 6, 8. On the next page, you will say what's your harmonic current order as a third, 5th, 7th. So all harmonics, even harmonics, are in a different table. What I typically do was that once I got those test reports of the harmonics, I will use Excel to convert those PDF files to the Excel spreadsheet in a format like this. Because once I do that, you can say this is my odd harmonic order and this is my even harmonic order, right? It's just copy paste, manually copy paste, or using Adobe Professional to convert it to the Excel spreadsheet, and then you run the percentage comparison or percentage conversion to convert the ampere to what's the percentage value of the harmonic current injection at a particular harmonic order, because that's the input of EasyPower, right? And then you summarize them together to become your harmonic spectra injection table. So that is the input of your harmonic study for each inverter as a harmonic spectrum, right? So you got your power flow model, you got your harmonics model, that's all you need to get started. Now, we do have everything we need to get started, so let's get started on EasyPower. Let's see if we can construct the power plant in about half an hour and run some tests, right? So first of all, you have your utility system. Now, we know that from the one line, we know that my utility is 115 kV, right? So my utility bus voltage is going to be 115 kV. Put the bus here, 115 kV. And the strength of your system is the crucial number to put, because still according to the IEEE 519, as you can see from the violation table or criteria table, it contains short circuit ratio. So based on different short circuit ratio, the ITDD limit is different, right? IEEE 2800 does not have that. IEEE 1547 does not have that either. But if you still want to go with IEEE 519, then this number is still vital to evaluate any standards violation, right? So typically what we do here is that again, it depends on the real system short circuit ratio, short circuit strength that you can get from your local utility. So I would say typically for a 115 kV system, I would have, let's say, 1100 as my MVA utility strength, right? For three phase, I would assume that the zero sequence is the same, that you have the similar three-phase short circuit level and single line to ground short circuit level, right? So that's what I use as my input. Now going downwards, oh, by the way, I did not put too much value on the XR ratio. Maybe 40 is a typical number we use as well, right? So we put a 40 as well. Now next step is to add a transformer. Before we add a transformer, let's add the generation interconnection line. Some people call that the gen tie line. So let's put a transmission line here. Where's my transmission line? Here is my transmission line here. And then the length might be very small. Let me just choose a random number to start with, right? And then because I will put a very short length to the gen tie line just for me to provide fictitious generation interconnection tie line from my high side of my substation transformer to the utility bus, right? So, oh, EasyPower only allows 0.01. Okay, that's it. And I will put the high side of the main power transformer bus, drag it longer. Now I put the transformer over there. So for transformer, I know that my high side is 115, low side is 34.5 kV, right? Drag it longer. And usually the connectivity is YG, Fury delta for the transformer, right? So I will enter the transformer parameters. What do I have here? My NV base is 57, right? 57. My impedance is 8.5. X-bar ratio is 31.5, right? From the number here. So 8.5. X-bar ratio is 31.5. And my Z0 is 8.5 as well. Okay, that's my transformer model. EasyPower does not complain, which means that that's a full set of the parameter we need to model transformer, right? Now, let's go down to the cable, collector system cable, and put one cable here. Go down. Put a bus here. Now, this bus would become my GSU high side bus, right? So I put my GSU here as well. For the length of the collector cable, since we have the contract with our clients that we cannot, release the proprietary information in our webinar, so I just assume that okay, the length of my cable is 1,000 feet, and the design is XLPE 350, right? Just a base assumption we make over there. So, and we do have the main power transformer and the base, which is according to our data, power flow data, right? The solar inverter step-up transformer, 3.6 MVA, right? 3.6. Let me first create the bus first, otherwise it will complain. Level is 0.6. Is that 0.6 or is that, yeah, it's a 0.6 kV, right? The output voltage of the solar inverter. So 0.6, that's my inverter terminal bus, right? So I have my transformer impedance, which is solar inverter step-up transformer impedance as 6.5, X-bar ratio as 8, right? So 6.5, X-bar ratio as 8, 6.5 as well. I don't have to enter X-bar ratio for zero sequence because it's equal to the positive sequence according to the data, right? So put it OK as well. And now I want to enter the inverter data. Then I need to drag the whole thing down to leave me some room to put the utilities, I mean DC utility source, right? And what's my KVA? The KVA solar inverter is here. It's 4 MVA, which is 4,000 kVA, right? XR ratio usually is very large, so we can put let's say 99 over here, right? And definitely it's an IGBT inverter, right? Power flow, I would like it to be a voltage control, which is a PV bus, right? You want to control the voltage is 1 per unit. Kilowatts is according to the power factor 0.855. I would say it's about 3.5 megawatts, right? So which is 3,400 kilowatts, right? And my kilowatt mean, I would say multiply by 0.5. That's about 90%, I mean 90% power factor, right? So you multiply your kilowatt by 0.5, which is about 1,800, right? Kilowatt. And that's all. That's all you need. Click on OK. I know what my data is missing because I did not add my DC utility as well, right? Now, some people would like to add the DC side as a PV panel, which is okay. But be careful when you add a DC PV panel, you need to be very careful to calculate your maximum power tracking point voltage and the operating current and the maximum power rating. So we don't want to focus on that today because that's a lot of calculation involved. Or just use a DC utility source to represent, because at the end of the day, what you have is that you only want to study the interface from your AC output of your inverter, right, together with the utility. So you don't really care too much about how your DC side works when you study harmonics, because there is no harmonics in DC. Every input is an inverter, right? So let's try to solve the power flow first to make sure that we don't make any mistakes. Again, this is a typical experience we have had, that once you are done with a model in a certain stage, it's better to try out your power flow solution to make sure that there is no data entry errors and what your output is as expected. So what I have here is that 3.5 megawatt output. Definitely I have to select my one line output option as megawatt megavar. That's correct. And also solve the power flow. I can say that I have 3.5 megawatt come out. I have 0.298 megavar coming in because the voltage schedule I have here is 1 per unit, right? So okay, so power flow looks fine. If I scroll down a little bit to just make some room for the quality display. Okay, now I have my collector cable section of one inverter done. So the next thing we need to do is very easy in EasyPower, right? What we need to do here. Copy, paste, right? This is a typical fun thing to do in EasyPower when you construct one line. But looks like we are done with the power flow, but we are not done with the harmonics yet. So we need to enter the harmonics data and then start the copy paste. Otherwise, you will be missing the harmonic spectra in the inverter, right? So it's a good habit that you build the full model of the inverters and the system in EasyPower and then start copy pasting and those fun things. So let's enter it. I know that my harmonic source has been calculated by my Excel spreadsheet, which is here. So I just copy, paste it here. That's all. I'm done with my harmonic modeling because all those harmonic spectra information comes from my manufacturer, right? And I have converted from ampere to percentage, which is what EasyPower takes an input, right? So this is a full set of the harmonics model of my inverter and my one section of the collector cable system. So I keep adding things on. 1, 2, 3, 4, 5, and 6, right? Because according to my one line, this is my one line, I have 6 PV power blocks on the same collector cable, right? So I have to copy and paste 5 times to make it 6. And then I can copy and paste the whole 6. to become the second feeder of my plant, right? Copy, paste. It does not like my paste. I see, there is a small mismatch here. Okay, paste. Now let's copy it up. Still don't like it. Put it closer. Okay. 1, 2, 3, and 4. Okay, that. Okay, now I have 6, 6, and 5 because this is there are only like 5 inverters in total, right? I take it out. Okay, now I'm done with my power plant model of my PV portion, right? I just want to make it look good. Okay. So this is a typical power plant model we have had in EasyPower. So if we choose to solve the power flow, what we'll have? Okay, we do get our power flow. This transformer is overloaded simply because we put the rating as the MVA base, and we all know that usually the MVA base is much smaller than the maximum rating that you can go up to, right? So in this case, if we are done with this model, let's first ignore the battery energy storage portion and only build the PV portion. Then we'll see if we'll have time to build that because it's nothing but the same thing as copy paste the whole design, just enter different harmonic spectra, right? Now let's go back and put PCC breakers over here. Typically, we would like to put the PCC breaker right at the utility bus, right? Because that's where you connect with the utility. And then you have to enter some harmonics data. And so far, EasyPower 10.6 only monitors IEEE 519. In our EasyPower release 11, we would be able to monitor IEEE 519 with the standard as 519, 20, and 22. And in our later release, we'll add the option of using either IEEE 519 or 2800 or 1547 based on your needs. So let's for now only use 519. I have to enter kVA demand and the short circuit ratio. Okay. Now let's go to how do I get my MVA demand? Definitely solve the power flow will give my kVA demand, right? So my kVA demand is my output as branch kVA and power factor. So I got my kVA demand as 80470. 80470. Let's write that down just in case I will forget. Calculator. $80470. Okay. So what's next? That's my kVA demand. What's next? I have to go back to this edit. Click on this. Harmonics kVA demand is 80 megawatt, 80 MVA, right? Now, next quantity is calculated the ISA divided by the I load. So first of all, let's go to short circuit and apply the fault here. Say what's your fault kVA? My fault kVA is 5.5. Sorry, I have to clear it. 5.522 Ka, right? And what's my loading current? I load. I'll go to power flow as well. Solve it. Use my power flow option to show the branch flow as current in ampere, right? So this current would become my load ampere, right? This is my fault ampere, 5.522 Ka times 1,000. That will become 5522 ampere divided by my 404 loading current. So my short circuit ratio is about 13.6667, right? Okay, I got my short circuit ratio, and then I want to go back. My PCC harmonics injection is short circuit ratio is about 13.668, right? That's all I need. Now, if I go to harmonics, what do I miss anything? I have my power flow model which solves, right? I have my harmonic current injection spectra for every inverter. That's all I need, right? So I don't miss anything. Now I go to harmonics, run the summation. And then what EasyPower can do is to populate the IEEE 519 2014 report for you. Again, we will release the IEEE substandard 2020 standard in our later release immediately in our 11, sometime later this year, maybe beginning of next year. So you will see that once you have the new EasyPower release, you will see this IEEE standard as 2022. But if you still have some ongoing project, then you can still use the current version, which is 10.6 for your study, right? So it's a transition to the standard compliance. So I click on OK. Now I'm able to get, okay, what my harmonic injection violation report looks like. Definitely, I have my Ph.D. out of my range. Anything red in EasyPower means that, oops, it's a violation, it's a bad thing, right? We know that. And then according to my all the harmonic, even harmonic spectra reports of each individual and the total total harmonic distortion currents, I have my 6.13 violation as well, because the IEEE limit is very small and the even harmonics can go up to 6%, right? So this actually captures the whole process of modeling a power plant, IBR-based power plant EasyPower, and evaluating the harmonic performance for the project. We intentionally create some issues over there because there are some issues we have to fix. And the very simple fix, again, it's not a fix, but the fictitious for the purpose of discussion only is to increase your short circuit ratio of the utility, right? In a stronger system, then you should have a less problem like that. Or another way to mitigate that is very simple, that you design a harmonic current filter, right? At the 34.5 kV, so all those harmonic current will go through the filter instead of goes through the transformer, main power transformer, and go to utility and create your ITDD, right? Or the current distortion, harmonic distortion, right? So, or demand distortion, sorry, not harmonic distortion. Harmonic distortion applies to voltage only. Current is the demand distortion. So that is the whole process of evaluating the PV portion. Now, if you want, what we can do is very simple, that we just create the same process as we did just now to add the battery energy storage portion at the very right. So you copy and paste the design and then revise your harmonic current injection based on the energy storage inverter spec, and then revise the GSU rating and revise your inverter rating based on your power flow data for the BESS, right? So definitely your solar inverter MBA rating is 4, and your battery storage energy inverter MBA rating is 3.96, so that's the number you need to change. And the GSU impedance rating you need to change as well. At the very end, we are looking at energy storage, then you need to look at the energy storage portion of the harmonic current injection spectra listed in this way, right? And at the same time, it's just a working habit. I would like to convert this whole table to Excel spreadsheet, and in this way, right? So I have my harmonic distortion of my energy storage inverter in this way, and because it provides phase ABC, what EasyPower takes is the positive sequence. So what you can do is either calculate the average or the maximum out of the 3 phases. I would like to be conservative, so I usually use the maximum number to calculate, right? So that it's a max of all the 3 phases, and then I use this as my new harmonic current injection spectra for my inverter. As you can see, violation is valid actually, because at my 11th order, if we go back to the 4,000, at my 11th order, I have about 0.14, and its 13th order, I have 0.14 as well percent of the current injection, which is huge, to be honest with you. Together with the other quantities, you can see that the 11th order and 13th order are 5 times, right, or 4 to 5 times larger than the other harmonic spectra. And the IEEE limit, if we go back to the IEEE limit for the high order, oh, this is 519/2020. So let's go back to the 519/2014. So how do we measure it? If I go to my table here, that's okay. I have my harmonic order equal to 11 and 13 to be limited at about 2%, right? So which is very small, to be honest. So if you have so many harmonic current injections from so many inverters, that can aggregate together and become a violation as well. And also my high order harmonics, let's say higher than 23, the limit is even smaller. So it's very easy to cause violations as well. So usually what we typically do is to install harmonic active filter to absorb those harmonic injections for the high order, or install passive filter at a 30.5 kV to filter out. So usually passive filter works as a zero impedance path, right, to the ground to renavigate the harmonic current from flowing through the transformer and then flow to the ground. So that's a typical way. Now let's go back to our original question we have asked at the beginning, that why we feel like capacitor cut bank, which is typically used in the power plant for reactive power compensation, is not a good idea. So if we go to harmonics and double click this bus, which we know that will give us the frequency scan result, right? So let's make sure that my frequency scan setting is as appropriate. So plot output, I want to go from the first harmonic order up to 50, right? Step is 0.1, summation is 0 to 50 as well, and then click on OK. We know that, okay, in my system, I do have a resonance point at 21. What is my level here? About, if you go to the left, you will see what exactly is the value, right? Okay, I do have a resonance point around my 21 to 22 harmonic order, right? So if I have 21, 22 harmonic current injection, it will be significantly amplified because I do have a spike here. And we know that the spike is caused by what? It's caused by the registers or capacitance provided by the cable, because we have a collector cable system, right? So in this case, we know that any capacitance between the phase and the ground would cause resonance point. And then we already have the resonance point introduced by the registered capacitance for all the cables I have. What will happen if I still need to insert a cap bank here? Let's say I insert my cap bank. Where is my cap bank? Here is my cap bank here. Let's say not too much, 10 megavar, right? So you are actually inserting or injecting more capacitance from the phase to ground, which means that there will be some shifting of the resonance point and maybe amplifying the resonance point in some case, right? So if we add a capacitor over there, go to harmonics, double click, you will see that the resonance point has been shifted to about 6 or 7 harmonic order, which is even more severe, right? If we leave this, take a snapshot of this. Because you insert new capacitance by the new cap bank, right? Remember what we have just now. If I open this one, my resonance point is about 21, 22 harmonic order, right? But after I introduce a new capacitor, I have shifted my resonance point to the 6th order or the 7th order harmonics, which is a big change of my system frequency response, right? And that actually could introduce more problems at the lower order of the harmonics. So you will have lower order harmonic violations if your inverter is going to inject current, harmonic current at the lower harmonics, right? So that is why many people still like to design capacitors as a reactive power compensation to comply with the FERC order 829. But actually, you have other concerns as well. When you introduce a new resonance point to have harmonic issues, for 2800, it may not be such a big issue. But if you still is using the IEEE 519, considering the system strength, you may have an issue. Even with the 2800, you may still have an issue as well because you introduced those resonance points, right? So it's possible that you will have a higher voltage and eventually have a higher current demand distortion at the 5th order, 6th order, and 7th order. I mean, it depends on how large the compensation is, right? You can see that the larger capacity you put over there, the closer you are to the fundamental, right? So this is what we have learned in our past studies as well, and this is what we want to broadcast the message. In fact, it's an industrial practice that do not install too many capacitors at the 3425. If you do, please install together with some harmonic filters at the IBR, right? So those are what we have prepared for today's webinar, including from the data collection that you collect the one line, and then you collect the power flow data for the main power transformers, for the GSU, for the inverter sizing, and most importantly, ask the manufacturer for the harmonic current injection spectra, right? That's all. We can have all the data we need to build our power plant model like what we did just now. How much time I used? Pretty much only half an hour, right? To construct my PV portion. Then you construct your BESS portion as well for another half an hour. So most likely this whole work will take you about, at most, I would say 2-3 hours to finish up in EasyPower. I would say that's a very efficient way to evaluate. I know that many of our clients use PFCAD, EMTP, those kind of time domain software to evaluate the IBR, to build an IBR in this PFCAD model and run the harmonic analysis or even the other analysis, which is accurate, but you don't have to do that if you obtain this table, right? Most importantly, this table, and also the injection table here as well, about what's the designed harmonic injection level at a particular harmonic order. If you have this, you got all you need to use EasyPower to finish this job within maybe just whole morning or afternoon, you'll get it done, right? Okay, so I think that's all for the presentation part. We are at 10:45 almost, and we can switch to questions to see if you have any questions pop up.
Yeah, we have a couple from Zaid. Can you see the question list?
Yeah, I'm able to see the question list, but I'm having some, okay, now I can drag it down. I'm having some technical issues playing with GoToWebinar. So let's start from the beginning. Sorry, I think I missed this part, but which standards we have to follow now? That, again, that question I mentioned at the beginning, there are so many standards out there. It's just the standard you have to agree with the utility to follow. IEEE 519, IEEE 1547, and IEEE 2800 are the 3 typical standards in the United States, right? The second question is that if there is a capacity in the system, should we model it or not? The answer is it depends. So it depends on if your capacitor is far enough around POI and your utility system takes that into account or not. So what we studied here is that we only care about what the PCC harmonic demand distortion, right? And the distortion within our own system. As long as you have established agreement with that, then what the project scope will be determined, what's the current injection at your PCC, but not with your system. However, if you want to be a good citizen, say, hey, we would like to say because we have this capacitor in our system creating resonance points, then our standards established at the standard, our criteria established at the PCC may be different or maybe more stringent than IEEE standard, right? So that's when you may want to consider model more details or more layers of utility system instead of only using one source, right? A third question, why we have 3366 in the Excel sheet? Good question, because many utilities, many manufacturers would consider not only the current injection level at 100%, at 33% output level of your inverter, you may still observe a significant amount of current harmonic injection at the inverter, even if your fundamental current is smaller. So it might be more sensitive to have, or it might be more sensitive to see what is your ITDD level, or especially Ph.D level, right? when your system output is lower than it is designed. So that is why many of the manufacturers of the inverter provide different harmonic injection limit or different operating level of your inverter output, right? So how to set the standard we want EasyPower to follow in EasyPower? So far, we do not provide the option because IEEE 519 just released in August. You got to give us some time to design the, obviously, new standard compliance with you, right? Some of our customers do it in the way that they build the IEEE 519 report or they build the violation matrix by themselves. It's very simple, actually. I'll show you. If you don't know which standard to comply with or the standard you have to comply with is not IEEE 519, what you can do is go to Harmonic reports and select summation spectra report and detailed report. Click on OK. So do a summation. What you will get is which branch we're looking at is the branch. Is a transmission line cable name. It's easier to do it in Excel, so you dump it to Excel. See if you can find a transmission. There we go, transmission line. So this is the transmission line current distortion. Just compare those quantities with the limit. That's it. That's all you need to create your own report of violation, right? You don't have to use EasyPower IEEE 519. It's just, I would say, a master sheet of, say, of indicator that if you have violation or not. If you want to go to detail, this is the quantity you use to find out at which harmonic order 22. That's what we discussed, right? Because we have resonance point at the 22nd harmonic order. So that's how I found out, okay, at which harmonic order exactly I have the violation. So if you don't know which standard to comply with, just choose agree with your utility and choose which current to be used and compare against, right? Okay, next question is AC to DC. Should I be worried the harmonics or DC portion will stop the harmonics from the transforming to the other AC side? Again, AC, DC, AC, I don't think that's a problem because all the utility cares is the AC interface that it can see. So what's beyond it, it's not a harmonic issue, right? Next question is the harmonic source. We have currents or voltage harmonics. How to control this? Usually in EasyPower, we only model current injection. So if you want to model harmonic voltage source, I think we have other webinars to discuss how to do that. So it's up to you. Not up to you. I think it's up to the manufacturer that if the inverter would provide you as a current injection model or voltage injection model, then you can pick and choose, right? Next question is, I think all these questions comes from Daid. Anybody else has any question? Okay. The next question is, to perform harmonic analysis, it is very important to get data of the harmonic order. And interharmonic sometimes are going to IDC from SMA, Huawei, Grot, Fronos, and other sometimes did not deliver such data. What do we do? Well, keep asking. We cannot. The story is very funny. We cannot. Many people ask us, hey, how can EasyPower do it? We cannot. The reason is very straightforward. If you want to have this data, you're going to have to sign NDA with the manufacturer, right? NDA means that those information are proprietary to every manufacturer of the inverter because those inverter manufacturers may compete with each other saying that, hey, the GE inverter, oh, GE is no longer in the business, sorry. Maybe Huawei's inverter behaves in this way, then why SMA cannot do that? Or based on the harmonic, I would say, spectra, they can back engineering about what other people are doing. So that's why, when we share those information, we need to be careful that do you have an NDA with them. So that's why we cannot put those harmonic injection data in the EasyPower library. It's not like some public information. It used to be, but now it's more and more stringent. The IEEE standard 519 now indicates the DER and inverter-based resource. instead of follows applies applicable instead of F19. Is that a comment? Yes, it does. So that's why we said at the beginning which one to use, right? And does EasyPower have this option? Not for now. 10.6 released before the new IEEE 519. If you go to 11 and onwards, we're gonna release 11 later this year, maybe early next year, and later on you will be able to see that we will allow you to enter choose multiple standards to comply with, and eventually you can choose which report you want to get. Does EasyPower have this option? Yes, it will be in the future, but not for now. Could you please describe again how harmonic injection spectra was extracted from manufacturer's harmonic test data? I think what you can do is to review the slides. I think we still have some questions. Sorry about that. So I want to go over the questions. Are those limits supposed to be individual, not combined for individual harmonics? The answer to that question is yes. The IDD demand, the current demanding distortion is individual and total, two criteria. So you're gonna have to comply with both criteria, both individual and total. What's the difference if we check harmonic using EasyPower or transient analysis such as EMTP? For example, the filter sizing will be different. Now, there is no, they behave identical. It's just the EasyPower is the frequency domain analysis, and PSCAD, EMTP, RV, or ATP is the time domain. So they use sinusoidal waveform. But at the end of the day, if you study harmonics within 50 Hertz, I would be really surprised if you can conclude something different by using two different approaches. Do studies need to be a detailed model of the collector and inverters, or can you get by equivalent collector and inverter model? The answer is you have to model every inverter specifically. What we're doing is harmonic study. It's not a short circuit study or power flow study or stability. So we have to model the power plant in detail. The reason is very simple and straightforward. Go back to EasyPower, you will see that every cable registered capacitance. So it behaves at two ends that you will have a voltage booster or current path to the ground, right? So the network solution of the detailed model is totally different from the equivalent model. For short circuit, it's not the case because the cable capacitance is negligible, right? You won't have any path from phase to ground for fault current from the registered current, from the registered capacitance. But for harmonics, yes, it's prominent to have those capacitance modeled in the explicit way. We said that at the beginning, right? The Jerry Bond. Next question: manufacturer provides harmonics for each phase. Do you use a maximum? Use maximum. Sometimes we use average as a positive sequence average, but I use maximum, and I recommend to use maximum to be conservative, right? Champark. If I have 5 inverters, each 2 MVA to get 10 MVA conversion versus 2 inverters, each 5 MVA, both meeting IEEE 519, is this less number of inverters get you better Ph.D. results? Do the study. I cannot see that. It depends. What is the Ph.D. at the TCC with the 10 megavar cap bank? I think Ph.D. was 10% without the cap bank, and I would like to say the Ph.D. change. Yeah, sure. So let's go to harmonics summation. The level 10% is without the capacitor. With it, you will reduce it significantly to 1.311. Here we go. So possibly you filtered out some of those harmonics. But again, it depends on where your harmonic spectra. You're lucky here because massive amounts of your harmonic injection are at high harmonic order. So if you move the oscillating point away from the high harmonic order, then you avoid the problem from the high harmonic order. But in some cases, if you have, let's say, harmonic current injection at the 5th order, 6th order, then you will have a high oscillation problem, high voltage, high VTHD problem, right? So it depends on the spectra of your injection, where exactly you have the problem, and the system characteristics about where exactly is your resonance point. You do not want to put your resonance point, system resonance point, right at the largest amount of the harmonic current injection place, right? So this is more about do the study and then find out if you can mitigate the problem or aggregate the problem. Does EasyPower support frequency scan for transformers? I think the idea of frequency scan applies to the system. So if you only want to say what's my frequency scan result of a transformer, then I can tell you right now it's a linear response, period, because that's the transformer model we have, right? I mean, that's a transformer model of the in all of the frequency domain analysis tool, right? So if you apply the frequency scan on this transformer only, then it's just a linear line. The question is that if you're talking about the frequency scan, it definitely has to be the whole system. But starting from bus 3, what's my frequency scan result across my whole system, right? EasyPower has a current angle column for each harmonic. How important is that? Enter. That is very important. And most likely, if you don't have that information for a manufacturer, enter 0 is okay. We all know that if you enter the different power angle of the harmonic current for different sources, it's possible you aggregate or you cancel each other, right? So it's a vector sum of all the current source, not the scalar sum. That's what we need to keep in mind. That's a great question. That's what we need to keep in mind in EasyPower. Very helpful. Hope to see more webinars. Thank you very much. Well, any presentation materials? Answer is no. We cannot share any of the webinar material today with any of you, but you can come back and watch the video. It's okay to watch the video, but we cannot share any of the information with you because they are proprietary. Even for the one line, it's risky because it comes from one of our clients. I just took out the name and the project. The manufacturer, I have to keep it. It's SMA, but please don't quote on me about the manufacturer data sheet. SMA keep changing this inverter injections. Again, always get the latest and greatest data from the manufacturer of your harmonic current injection, all right? Can the background harmonics of the grid also be taken care of? The answer is yes or no. Depends on how detailed you model your utility system. For instance, what we have modeled here is that we have only one power plant. EasyPower supports co-simulation. That's what I like EasyPower the most, is that it can model both transmission and distribution and industrial application at the same time. So if you want to put your transmission system models over there, EasyPower is able to handle that. There is no radial connection, I would say, requirement for EasyPower harmonics. You can feel free to add looped network in the transmission and then add different places with different harmonic injections from different power plants and aggregate them together to be a combined model and study, which is very neat, but it's very comprehensive as well. So capability, yes, just be careful about the penetration level of your harmonic sources along your system and model the system size properly, right? CEU, that question goes to Jim. I don't think we provide CEU, right, Jim? Do we provide CEU?
We provide an attendance certificate that most people use to support their ECU credits. They'll get that by email.
Thank you very much.
Yeah, and for those of you that came in late, we'll be posting this video to the EasyPower website. You'll receive a notice with a link probably early next week. Great job. Thank you, and we look forward to presentations in the future, Tao. Thank you very much.
Thank you, Jim. Thank you all. See you later.
So long.